This is the capacitor board, and this was basically homemade by our physics department for under $100. We cut off pegboard, we bought the inserts and the hooks, the capacitors and the resistors and the LEDs came from China. We actually found LEDs that had specifications so we could use them in our more advanced experiments for cheap, 50 cents a piece. We have a light holder here and a 1950s capacitor, and we have a series of resistors. All in all, excluding labor time, this board maybe cost $10, and you can do a number of electronic experiments on it. It could actually be built by a guy that's handy for perhaps less than that. Okay, so in this case, what I'm trying to do is to measure the capacitance individually, in series, and in parallel. And this particular multimeter has a capacitor setting, so I can actually measure the capacitance of each of these 5 capacitors, which we bought with 5% plus or minus to be 100 nanofarads. And as you can see, this is registering 112 nanofarads. So that means we got ripped off. So I would measure each of these 5 individually. And then I would put 2 in series, in which the capacitor would go down, because effectively we're lengthening the distance between the first negative plate and the last positive plate, until I've got basically 5 capacitors in series. So on this particular board, that's exactly what I've done, because it takes a little time getting everything set up. So as you could see, I would be going from this capacitor to here, through this one to here, from this one to here, and my multimeter would be set at these 2 positions. And so I should be reading roughly 1/5 of the value I recorded if all the capacitors were in fact equal. Okay, so where did that go? And it takes a bit, and I'm recording 20.5, which is about what I expect. To do this setup, to go through each of the numbers, takes a while, but obviously in this setup and demo, I want to do it in a shorter period of time so you can see what in fact it looks like. Again, these small ones came for under $30. This multimeter is about 100 to 150. Okay, then you would want to do the same thing again with those same capacitors in parallel. In parallel, we're effectively adding the plate area. So as we do that, the capacitance could go up. So these happens to be 5 capacitors in parallel. So if I touch them over here, putting one end right here again, and touching the other right here, I should see over 500 nanofarads. I get 571, and that makes sense because they all seem to be a little bit more capacitance than we ordered. So capacitance adds in parallel. There are diagrams in the PowerPoint and in the lab manual on this. Now, you also want to look at this 1950s version of a capacitor, and all you need to do is clap with these 2 ends right here and take the reading, which will be between 300 and 400, because we in fact don't know what it originally rated at because it's over 70 years old, but it still holds a charge, which is kind of interesting. At the bottom here, you see a battery holder, and we found out if we put 2 batteries in, it would go over our ballistic galvanometer. So you want to change a 2 battery holder into a 1. You simply jump the leads from here to here. Okay, so how did they do it in the 1930s when they didn't have such a cool thing? We would want to check this decade box against this capacitor to see how they rate to each other, because this is rated in 500, 400, 300, 200, 100 nanofarads. And as we found out when we measured the 2 against each other, they did not agree. So the question becomes, was this precision equipment that is roughly 20 years old more correct than the multimeter? How would you determine that? So we're going back to how they did this in the 1950s to the 1930s when they wanted to measure capacitor. They had known values based on the construction materials and everything like that. And so in this case, they would dial in the capacitor value they had here. On the other side, they'd have a battery. And on this side, we have what is known as a ballistic galvanometer that you can't see. So I'm going to push it in a little closer so you can see it. Now, in this light, you can't see the light, but when I charge and discharge, it will swing that way. So what I'm going to do now is turn off the lights and bring down the shades so you can see when I charge and discharge, this light will be thrown. Based on certain standard values, I can make a slope curve so that I could do the same thing with these boards and get a value based on this older setting. And then I could compare 2 different methods of calibration, which is my point. How good is your calibrator? Okay, you can just see the light now. It's fuzzy, I admit. So I have charged, and now I'm going to discharge. And you see it went over and it came back. Charging and discharging at the nanofarad range is very, very quick. We have another one that's called RC circuits that takes a little longer to do. But in fact, you can develop a decent calibration curve using this technique. So we would do 500, 400, 300, 200, 100, set up the curve, and then we replace the decade box here with the capacitors in parallel, the capacitors in series, and our old 1950s capacitor, and get a number there. And we would use the idea of slope and intercept.